On February 11, 2016, the Laser Interferometer Gravitational Wave Observatory, or LIGO for short, announced that the gravitational waves had been directly detected for the first time. So what are gravitational waves and why are they so important? About 100 years ago, gravitational waves were predicted by Einstein's theory of general relativity. According to Newton's theory, gravity is described as a force between two objects. Whenever an object with mass changes position, the gravitational field associated with that mass will change too. However, there was a big problem with Newton's theory of gravity. It predicted that this change in the gravitational field would happen instantly. This meant that the information carried by gravity could be instantly detected over an infinitely long distance. That is, according to Newton, gravity had to be faster than the speed of light. Einstein's theory was better in this regard. The theory says that space-time can be curved, and that gravity is a result of that curvature. According to relativity, the speed of light puts a limit on how fast an influence can travel through space, including the influence of gravity. Imagine now that you drop a pebble into a pond. You should see ripples moving outward in the water from where the pebble was dropped. Roughly, gravitational waves are much like the ripples in this pond. Just like how ripples are disturbances in the surface of the pond, gravitational waves can be thought of as disturbances in the gravitational field of an object. The important consequence of this theory is that if an object moves, we no longer predict that a change in gravitational field can be detected instantly. Instead, it now takes time for us to detect this change in the form of gravitational waves from the object that has moved.
So how were these waves detected? It is impossible to detect by measuring distances, since it is the space-time itself that is being warped when the gravitational waves propagate through space-time. Through LIGO's interferometer, two black holes about 1.3 billion light-years away have been observed orbiting each other before eventually merging into one. This collision created gravitational waves that were detected by LIGO here on Earth. Not only was this the first instance of direct evidence of gravitational waves, it was also the first time that the two black holes were directly detected before merging. So how does the LIGO work? There are two special facilities in the United States, one in Louisiana and the other in Washington State. Detector in each facility has L-shaped antenna with arms 4 kilometers long, and inside the ends of each arm, mirrors of pure glass are isolated from noise, heat, and vibration from the outside world. A beam of laser light measures the separation of the mirrors, and the beam is split and sent towards the mirror at the end of each arm. If the arms are of precisely the same length, the returning beam cancels each other out, and LIGO detector sees no light. But a passing gravitational wave would stretch one arm and squeeze the other. The resulting discrepancy in the wave detected is tiny, the fraction of a whiff of a proton, but enough to missile-line the beam and light up the detector in a rhythmic pattern. And on 14 September 2015, the LIGO detected a flickering light and turned it into a sound wave. It was the echo of the marriage of the two black holes happening billions of years ago.
What does this discovery mean? Why is it so important? For starters, just detecting the gravitational waves is a big milestone in itself, since even Einstein himself did not think it would be possible for us to detect them. Second, there is some interesting information from our detection of these gravitational waves. Analyzing these waves, we found that the angular momentum of the final merged black hole was slower than expected. This suggests that the two black holes collided at low speed or were in an unusual collision configuration. So right now we don't know why this would happen. So this might lead us to develop some kind of new physics or theorize about some new physics. Finally, having this information about gravitational waves allows us to examine high gravity phenomena properly, something that we haven't been able to do properly before. Of course, the eventual application of this discovery is uncertain, but just like how X-rays and radio waves were initially mere scientific curiosities, there might just come a time where we will eventually find some practical usage for these waves.